Hi, everyone. Today we're going to begin our unit on logic. And this first lesson is an introduction. And logic is a mathematical subject we will study to prepare to reach conclusions from given information which we assume is true. And we encounter logic everywhere in our life. For instance, candidates for political office often appear to have differing ideas of what is logical. They can use the same information to arrive at very different conclusions. The purpose of our work in logic is to learn some of the ground rules in reaching conclusions. And as in any other mathematical topic, like algebra, trigonometry, geometry, or calculus, logic is a mathematical system, and to develop a mathematical system, we need these three ingredients. 1, definitions. We have to start with the words that we define. 2, axioms, and these are statements we assume are true. They are so obvious. And then finally, we use 1 and 2 to prove other statements that are true. And these are called theorems. So we're going to start with definitions and perhaps a few axioms for today's lesson. And then slowly we'll get to our theorems. Okay, so why don't we begin? So in arguments which use logic, we begin with a statement. And in the do now, I have a few sentences, and let's identify which ones we would consider true or false. So in number 1, 5 hundredths is 5%. This is true. So this is considered to be a true statement. 3 plus 4 equals 6. That's false. Okay, so we could definitely say that that's true and that's false. However, if we consider the other two, 3 says he sits in the back of the room, and 4 is y minus 3 is less than 10. These are not statements because we cannot describe them as true or false. It all depends on who we replace he with and what number we replace y with. So these are called open sentences. So this is neither, and this is neither. And the part that's open, like the word he and y, are called variables. So let's just define this. Before we go on. So our first definition. So we're starting with the definition now. Definition. A statement is any sentence which is true or false but not both. The truth or falsity of a statement is called its truth value. So in statements, we will always consider the truth values. Now, the placeholders in mathematical sentences are called variables. And an open sentence contains one or more placeholders which are called variables. And a variable may be replaced by any member of the domain. And the set of all replacements from the domain that make the open sentence true is called the solution set of the open sentence. And we've been studying this in algebra all the time. So the set of replacements from the domain that make the open sentence true is the solution set. Okay, I don't have room from my end to write this in along the bottom. So, okay, so these are things we already know. So a variable may be replaced by any member of the domain, and depending on what we replace, the open sentence becomes true or false. But we want to make the open sentence true, and that set is called the solution set. So, for example, the variable in 3 is he, and the variable in 4 is y. So if I use the domain, the set of all students in this 8E class, depending on who we pick for he, we could make this open sentence true or false. And in number 4, if our domain was the set of integers, depending on which integer we pick and replace it with y, we could make that open sentence true or false. Okay, so that was just a brief review of what we mean by domain, solution set, and a statement. Okay, but the key word is that a statement is a sentence that's true or false. Statements are the building blocks in a logical system. A convenient way of referring to a simple statement is to represent the statement with a letter, such as P or Q. Okay, for instance, let P represent Arizona was admitted to the Union in 1892. Okay, so whenever we see P, we'll assume that this is the statement. So if we want to negate this statement, we would say one of two things. Arizona was not admitted to the Union in 1892, or we could say it is false that Arizona was admitted to the Union in 1892. So when we negate a statement, in mathematics, we put what looks like a tilde, and we read this as not P, which is the negation of the statement P. So not P is called the negation of P. And now let's look at the truth values. The truth value for P, that Arizona was admitted to the Union, is false. Arizona was admitted to the Union in 1912, I believe. I hope that's correct, but I believe that's false. So if the original statement P is false, then what would be the truth value of its negation? Well, Arizona was not admitted to the Union in 1892 would be true. So here we have our first axiom. And remember, an axiom is a statement that we assume is true because it's so obvious. That if we start with a false statement, its negation would be true. And if we started with a true statement, its negation would be false. So let's write that down. So axiom, wrong color again. And I'd like to keep track of our axioms. Okay, this is our first axiom. The negation of a true statement is false, and the negation of a false statement is true. And in mathematics, in logic, what we do in order to summarize this axiom, we make what is called a truth table. So this is a truth table for the negation. And what a truth table does is that it lists all the possible truth values of a particular statement. For instance, if we start with P, a statement, that statement will either be true or false, right? Because that's how we define the statement. When we negate the statement, not P, well, if the original statement is true, then its negation would be false. And if the original statement was false, then its negation would be true. So this is the truth value for negation. Okay, but let's extend this a little bit more. If I negate not P, well, then I look at the previous problem, at the previous column, and if not P is false, then when I negate it again, it would become true. And if not P is true, when I negate that again, it would become false. So I directly look at the previous problem. And then if I negate this again, a triple negation, again, I look at the previous column. So the negation of not P, which was true, would become false. And then if I negate not P, I get true. And so forth. And I could continue. And hence now we have something really special. P and the double negation of P exactly match in truth values. We say that they're logically equivalent. In the same way, the negation of P matches the triple negation of P. Those are logically equivalent. When their truth values match exactly in the truth table. So let's define that on the next page. So logically equivalent statements are two statements that always have the same truth values. And the symbol for logically equivalent looks like an equal sign, but there is an arrow on each end. And we read this as logically equivalent to. So on the previous page, we proved two logically equivalent statements. P is logically equivalent to its double negation, and not P is logically equivalent to its triple negation. And this reminds us of a property with integers. When we negate a number twice, we get back the number. And when we negate a number 3 times, we negate the answer. We get back -2. So this is a rule that can be generalized into an even number of negations will give back the original truth value of the statement, and an odd number of negations will negate that statement. All right, now we're ready to look at our next kind of statement. Actually, 2 statements that you're all familiar with. And I'm going to introduce these 2 simultaneously. These are called compound statements. They are formed by taking 2 simple statements, which we'll call P and Q, and putting them together with a special word. A conjunction is a compound statement formed by joining 2 simple statements with the magical word and. That's called a conjunction. A disjunction is a compound statement formed by taking 2 simple statements and putting them together with the word or. So and or play a very, very special role in mathematics, as you've seen last year when you studied union and intersection. But be that as it may, let's take a look at the truth values of the simple statements and then determine what the truth value of the final compound statement would be. And these will be axioms because these are statements that we'll assume are true. When and should be true and when or should be true. So let's find the truth values of the little simple statements. 2 is less than 5 is true. So I'm going to put trues next to that every time I see it. And 2 is greater than 0 is also true. 5 plus 3 equals 15 is false. And we've got 2 greater than 0 here, so I'll put a true there. And -3 times -4 is -12. That's false. So I made these alike deliberately just to show you the difference between the final truth values, and then we'll summarize them in a truth table on the next page. All right, so when these are called simple statements, we found the truth values of the simple statements of the compound statement. Okay, so these are simple statements. And the final truth value of the compound statement depends on the truth values of its simple components. So let's look at it. If we have a true and a true, then I think we all agree that the final truth value is true. If we have a true and a false, then in that case, true and false would be false. We cannot have both at the same time. Similarly, if both simple sentences are false, then the final compound conjunction is false. And then if one is false and the second is true, we will say that that's false as well. And is a very, very demanding connective. Both have to be true for a statement with and to be true. Now let's look at or. The word or is flexible. It could be one or the other. So in number 5, the truth value would be true, the final truth value, true or true. True or false is true because one of them is true, and we're flexible. False or false would be false. and false or true would be true, because again, or could be one or the other or both. So now let's summarize these with axioms on the next page. First, we define a conjunction is a compound statement formed by connecting two simple statements with the word and. And our axiom is that a conjunction is true in only one case, when both of its conjuncts are true. Otherwise, it is false. And I didn't define conjunct. Each simple statement is a conjunct. So the truth values that we found in the beginning, these were conjuncts. All right, so the truth table, to summarize this axiom, for a conjunction we need two simple statements now, P and a Q. Just turn this off. And our last column will be P and Q. And the symbol for and is an upside down V. So we read this as P and Q. That's the symbol for a conjunction. All right. Now let's look at the truth table that we had in the do now. We had 4 lines. Okay, and let me just make this a little neater. So I'm going to reorganize them as follows. I have a true and a true and a true, a true and a false and a true, and a false and a false. And notice the order here. There are 4 possibilities when we put 2 simple statements together with a connective. And it's like a tree diagram. So when we have the first statement, P, that could be true or false. And when we have our second simple statement, Q, that could be true or false. So by the counting principle, we see that there are 4 possibilities. And if we wanted to list all possible combinations, we could make them as ordered pairs. True, 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 false, false, true, and false, false. But we list them this way in the truth table. And to summarize the axiom for the conjunction, we know that a conjunction is true when both conjuncts are true. So we put a true here, and otherwise the conjunction is false. And if we extend this truth table, we could ask, is a conjunction commutative? Does order matter? Whether Q goes first or P goes first. And you can see that if we look at the P column and then the Q, or the Q column and then the P, and reverse the order of the truth values, it does not affect the final truth value of the conjunction. So here we just proved our first theorem. A conjunction is commutative. And because the truth values match in the truth table, we could write that P and Q is logically equivalent to Q and P. And this is proven by the matching values in the truth table here. So a disjunction is a compound statement formed by connecting two simple statements with the word or. And each simple statement is called a disjunct. So in the same way, we have our axiom, which is a statement we assume is true. And we say, a disjunction is false when both disjuncts are false, otherwise it is true. Another way to say this is that a disjunction is true when at least one of its disjuncts is true. So as we said, or is a flexible connective. It's very easy to make a disjunction true. The only way to make it false is when both of the disjuncts are false. All right, now we have the truth table for disjunction. So let's summarize this axiom with a truth table. And again, we have P and Q, and P or Q, we read this as P or Q, is a P and it looks like a capital V. And again, we have true, true, false, false, and then true, false, true, false. So the only way a disjunction could be false is when both are false. Otherwise, it's true. So a disjunction is true most of the time, and a conjunction is false most of the time. And in the same way, if I extend this one more column, we could investigate whether or not a disjunction is commutative. So whether we look at P first and then Q, or Q first and then P, the truth values will match. And we see that these are exactly the same, and we have our next theorem. Actually, I should write this word out for you. Theorem is spelled this way. Our next theorem, which says a disjunction is commutative. And we could write that as, okay, and I'll write it up here. P or Q is logically equivalent to Q or P. I wanted to spend a few minutes and review how the logic comes in with algebra, and we've been using this all along, but I wanted to highlight it again. So if I asked you to solve these compound inequalities in algebra and sketch the solution set in the set of real numbers, you would solve each one individually. So here we get x is greater than -3. And since we have to divide by -3, we flip the sign. And so this is x is greater than -3, or x is less than 2. So we would write our solution set this way, but to graph it, we use the truth table for conjunction. Because when we graph this, we have the number line that looks like this. x greater than -3, we don't include the -3. X greater than 2, we don't include the 2, and we shade to the right. But when we combine these two, we want them to be both true at the same time. And they're both true at the same time when there's an overlap, which is right here. The overlap is here. So for and, the final solution set, and I'll make another. In the final solution set would be all x greater than 2. That's where they overlap. And that's when both are true at the same time. So this is the overlap. But when we have or, because or is flexible, we have to look at the region where at least one of them is true, or both. So there's a little bit of and or. This is when they're both true, right? This is where they're both true, the overlap. But then one of them is true here, and one of them is true here. So the final solution set for or would be all x greater than -3. So we would usually write our solution set in set builder notation as follows. For the first one, solution set is all x such that x is greater than 2 and x is in R. And the second one, for all the set of all x such that x is greater than -3, x is an element of R. And this may remind you a little bit of sets when we looked at union and intersection, because the union is or, and we have a U for that. The intersection is an upside down U. And notice they look a little bit like the and or symbols in logic, except they're U's rather than V's. And again, if we take a look at that, so the intersection of two sets would be the overlap again, that same theme. This is the intersection, whereas the union would be the union of the two. At least one is true. So we've got the overlap with A that's not in B and B that's not in A. And then the negation, well, it depends on what book you're using. Some books use a bar for the set notation. Some books use this, a little C in front of the A, but we read this as the complement of A. So the Venn diagram for that would look like this. If this is the world of A, the complement of A would be everything outside of that. So this would be the negation of A. So this is not A. And all of the theorems that we're going to prove with logic and truth tables can be done with Venn diagrams, as we will see in future lessons. What we have to practice in logic is to translate words into mathematical symbols and find the truth values of the final statement. So let's copy these in our books. Let P represent roses are red. All right, I'm going to assign a truth value for that statement. I'm going to say that's true. Violets are blue is Q. And let's say that's false. All right. And sugar is sweet. Well, of course, that's true. Now we would like to write in words and find the truth value of the final statement. So copy these down and translate these using symbols P, Q, and R and the correct connectives. So remember, when you see the word not, we're going to use the negation. When we see the word and, we're going to use the conjunction. And when we see the word or, we're going to use the disjunction. I'll do the first one with you. Roses are red. Well, that's P. And violets are not blue. So we put the and symbol, and not blue, we'll put not Q. And to get the truth value for that, well, I'll substitute the truth values that I have, true and not false, because Q was assigned to be false. Well, that's true, and the final statement is true. Okay, try the next two by yourselves. All right, let's try B. It is not the case that, all right, now let's make an agreement. Whenever we see the words, it is not the case that, we are negating the entire statement. So I'm going to put a negation and parentheses. It is not the case that roses are red, that's P, or violets are blue, or Q. Oh, I didn't even use anything about the sugar. All right, well, any case. So let's substitute. We get the negation of, now P is true and Q is false. And true, and we'll use the order of operations. Parentheses comes first in logic. So true or false is true, and the negation of true is false. And then finally, roses are not red or violets are not blue. So roses are not red would be the negation of P, and violets are not blue would be the negation of Q, but we have the word or, so let's see what we get. So we get the negation of true or the negation of false. That gives us the negation of true, the negation of true is false. The negation of false is true, and false or true gives us true. Now note that B and C investigates a very important property. It's investigating whether or not the negation distributes over the disjunction. And we just proved by counterexample that the negation does not distribute over the disjunction. Let's write that down. The negation does not distribute over the disjunction. So the question is, what does it do? We'll investigate that in the next lesson. All right, I feel like I have to give you a statement with R. So let's look at the next page. Okay, so in the last problem, I kind of put everything together in one sentence. The negation, the conjunction, and the disjunction. So let's look at it. Roses are red, and either violets are blue or sugar is not sweet. Okay, now note that I put that word either. And I want you to think about what that would imply as far as translating it using logical symbols. Try it yourselves. All right, so roses are red is P. And either violets are blue, that's Q, or sugar is not sweet, not R. But because the word either, we have an either or, this implies that this piece is together. Let's make that agreement. So we'll put parentheses around this. All right, that's just an agreement. Okay, so when you see the word either, or it is not the case that, we think of parentheses. So P is true, Q is false, and R is true, but we negate the true. I'm going to put everything in there like I'm substituting numbers for the variables. So following this, I get false or false. Then I find the value of the parentheses, that's false. And true and false makes it false. Okay, so now I'm going to end the lesson with the following question. Is the conjunction associative? In the same way, is a disjunction associative? And does the conjunction distribute over a disjunction and the other way? Does a disjunction distribute over a conjunction? All right, but here we have to review these properties with numbers before we could translate them in logical symbols. Well, the associative property of addition keeps the order of the numbers but shifts the parentheses. Well, the same is true here. We're going to investigate that if we have a conjunction, but this time we need 3 simple statements, is that logically equivalent to this? And in the same way for disjunction. Now, let's look at the distributive property. With the distributive property, we have 2 operations, multiplication on the outside and addition on the inside. So whatever operation distributes, it's on the outside. This is the distributive property of multiplication over addition. Okay, so if we look at the distributive property of the conjunction over the disjunction, it would look like this. We would have our 3 statements. However, if this distributes the conjunction over the disjunction's on the inside and the conjunction's on the outside. And we're asking, is that logically equivalent to P and Q or P and R? And here we need parentheses. So we could see the analogous situation with numbers. And similarly, for the distributive property of a disjunction over a conjunction, we have P or, now the disjunction's on the outside, the conjunction's on the inside, and we're asking, is that logically equivalent to P or Q and P or R? All right, now the question is, how do you make truth tables for these? Well, I'd like to discuss how many lines would a truth table have when we have 3 simple statements. Well, let's look at the tree diagram. The first simple statement will either be true or false, but whatever that simple statement is, the second simple statement will be true or false. And whatever those 2 are, the third simple statement could be true or false. Oh, I've put false here. This is a false. So by the counting principle, we have 8 possibilities. 2 for the first, 2 for the second, and 2 for the third. And the combinations are along the tree diagram. So our truth table would have 8 rows. So let's see how we would set up a truth table. So I'll set this truth table up and I'll leave all of those 4 questions for extra credit. So I'm going to demonstrate how to set up the truth table to show that, or to disprove that, the disjunction distributes over the conjunction. All right, so we start with our simple statements, P, Q, and R. And our goal is to build up our truth table slowly. So let's see what the truth values are. We know there are 8 possibilities, but this is the way we do it. We take 8 and divide by 2. So it would be 4 trues and 4 falses. This is an organized way to do it. Then we take the 4 and divide it by 2. So we list 2 trues, 2 falses alternately. And then we take the 2 and we alternate true, false. And all of these combinations I have listed are on the tree diagram that we have on the previous page. But this is an organized way to list all possible combinations for the truth values of P, Q, and R. All right, now how do we build our truth table? Well, we're going to start on the left side. And we always make columns for the parentheses. So we have Q and R. And then we're going to put that together with P or Q and R. So when we write the truth table for this column, we're going to look at the previous column. All right, now we're going to make a column for P or Q, a column for P or R, and then we put it together. So maybe I should go through this one at least so you know how to do it. All right, let's do it. But I'm going to draw lines to make this clearer. You have lined paper, but I'm going to draw lines so I could follow. Okay, I drew my lines. Now, I do this column by column. Don't go across because it's easier to find the truth values of a column at a time. So let's look at that 4th column, Q and R. So we look at the Q column and the R column, and we have and we know that and is demanding it will be true when both are true. So we look for 2 trues. This is true, and this is true. Otherwise, false. This is how I do it. Now, I go to the next column, and now what I'll do is I'll look at the Q and R column and combine that with P. So I look at these 2 columns, Q and R and P. And looking at those 2 columns, I have OR. So I know that OR is false when both are false. So let's look. When do we have 2 falses in a row? Well, the first row is true, the second row is true, the third is true, the 4th is true, the 5th is true. Here I have a false. And here is a false again. And a false again. Right? Because note that this is false and this is false. Oh, no, I did the wrong one. Sorry. I meant, this is what I do when I get my colors mixed up. Okay, so this is false and this is false, false, false. But all the others have a true. So I'm going to put down trues. Okay, same for P or Q. I look at the P column and the Q column. And because it's OR is false only when both are false. And this happens in the last 2, I think the last 2 only. So this is false and this is false. Otherwise, OR is true. And for P or R, I look at the P column and the R column. And if you have to point to them at the same time, it's okay. So I have true, 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 true. But this is false, this is true, and that's false. Because I have 2 falses there. And then finally, I combine these two with the word and. Let's see. If I put and between them, and is true only when they're both true. So I've got true here, true here, true here, true here, true here, but the others are false. And now I compare the left to the right. Notice that, okay, I ran out of colors here. Let me see if I could find another color. Well, I have gray. I guess I'll stick with gray. So notice that this column and this column are exactly the same. So we have just proven, using a truth table, that the disjunction distributes over the conjunction. Oh, I did the wrong symbol. And that is our first logic proof with a truth table, but a more complicated logic proof. So I'll leave the associative properties to you, up to you for extra credit, and prove that a conjunction distributes over a disjunction. It seems like it should. Try it yourselves. Okay, have a wonderful day, everyone.